Okay, so rates of change. This actually, in my opinion, it should belong strictly into a course in calculus, but it is in the advanced functions book, both in Nelson as well as McGraw-Hill. Okay, so it's something that they changed in these current release of the books. It wasn't there before, but it's in there now. So typically, I actually did teach it in the calculus course, but now I have to sort of at least mention it to you guys so that you guys are familiar with it in school. Now, let's say you have, we've been studying rational functions, we've been studying polynomial functions, right? So a function is graphically, right? It's a curve. And until now, we just sort of thought of an equation as a curve, a picture, right? But in calculus, you're going to have to start thinking about them as more as collection of infinite points. So really, we're taking a zoom and looking into, well, what's in here, right? What is this curve like? How did this curve form? Really form with all this infinite point. That's why we're able to, let's say, take the y value and the x value and say that right there belongs to a particular point. Let's say like 10 and 4, right? So every single location is a point. We just can't say them all because there's infinite of them, right? And you know that this such curve right here, so if this was a curve to a particular description of something happening, right, you know that as x increases, y first decreases, hits the x-axis, and then starts to increase again, right? So that's a very general description of what's happening here. In calculus, we want to say, well, not just is it increasing or decreasing, we want to talk about, well, how fast is it increasing, right? If this was a population curve, let's say this was population in Canada from year 2000, or maybe not 2000 too much, 1900 to, let's say, year 2012, right? Then you say, well, from here it was decreasing. Let me actually change the curve so that it equals like this. Okay, it was decreasing, and it was increasing, and it's continued to increasing. But where is it increasing faster? Okay, let me just drop up a region here. Was it increasing faster in this region A or in this region B? Right. Okay, do you see how it goes up much sharper at the same given length of, right? So if you were to actually measure the height here, look, that's how big the height is. If you were to measure the height here, do you see it's a little bit shorter? And x is about the same, right? So you can say that in the region A, increase faster. Okay, so this is sort of what we want to focus on. Now let me just give you some terms. So if you have a curve like this, okay, and then let's say we have A and B, and this is y equals f at x. If I gave you 2 points and I gave you a straight line, right? I ask you, what's the rate of change? Okay, that rate of change is just given by slope. Okay, so we're here, we move right this much, we went up this much. We call this moving up delta y, delta x. So the rate of change, okay, the rate of change between A and B, let's say between the 2 points, rate of change between A to B, we would say is delta y over delta x. Okay, so how is it changing here? What's the rate of change at this particular point A? Okay, the rate of change will be this. It will be equivalent to this slope here, right there. The thing is, we don't know how to find the equation of the slope or the value of the slope if you're given just 1 point. We need 2 points, right? So what we do is, instead of trying to find the value here, we estimate this slope value with this one. Now, I picked a point B. It's quite a bit further away from A. Okay. But do you see that if I actually brought B closer to A, right? Closer. Let's say if I brought B was here. Do you see that it would be a much better estimation? Okay, so let me actually draw here. If I pick B to be here, let's call this C actually. If I connected those two, so like that, do you see how that's a closer slope to this one than the one up here? Right? So we're in this section, we're just going to estimate the rate of change at a particular point. Okay. This slope here, so this one here, this we call here. We call that instantaneous rate of change. Okay, and this one here, we call this the average rate of change from A to B for the function y equals f of x. Numerical example. That's the picture. The main concept here is this. Really our ultimate goal in calculus later, because this is something they're going to focus on when you get to calculus. In advanced function, we're going to be dealing mostly with this, but we're doing this to later understand how do you evaluate an instantaneous rate of change.